All right, so let's analyze some stuff. Let's talk about polar coordinates. Transforming into polar coordinate system. Let's say maybe you have like, for starters, I like to start with the unit cycle. Basically, if you have this type of unit cycle right there, you're basically gonna let x be cos theta, and you end up with cos square theta plus sine square theta, basically giving us 1. So that's the whole key size idea. It doesn't really matter if you have x square plus y square equals r square, you'll still get the same thing. So basically in this case, like transforming to polar coordinate system, basically your x will be r cos theta. In this case, if you focus here, x will basically be r cos theta, and then y will basically be r sine theta. So now if we have this, basically this is a cycle. We all know that this is a cycle, and let's say you have a diagram there of that cycle right there. So you can draw a little triangle to understand what's basically happening. Then you have theta, and this will be your r, and this will be the x value, and that one will be your y value right there. But basically is that the coordinates at any point on the cycle will basically be given by r cos theta and r sine theta right there. So that's the whole point of the idea. This is x and y. Remember, coordinates are given by x, y. So right there, now we're transforming to a polar coordinate system. So remember, most of our double integrals are basically dx dy, right? Or dy dx, doesn't really matter. Dx dy dx, the order doesn't really matter of that. So basically have our double integrals in that form. So since now we are transforming to polar coordinates, let me first take you to use substitution first. Maybe like, let's say you have the square root of 1 minus x squared dx. Whenever you have like this type of integral, let's say 0 to 1, basically it's a trick substitution type of question. You'll basically let x equal sine theta. So if you let x equal sine theta, what you need is to express dx in terms of d theta. That's the whole point of this. So now when we're here, since we're transforming to r and theta, we're going from x and y. We're going from x and y to r and theta, So we need to express dx dy or dy dx in terms of dr d theta or d theta dr. Okay, so if we have this, that x equals r cos theta and y equals r sine theta, basically you can just work out your derivative right there, that dx dr, this will basically be, you just derive dx dr. The derivative here, you're going to have a product rule. You see that? You're going to have a product rule right there. So dx dr, this will basically be the derivative of r, it's 1. So you're just going to have cos theta plus r. The derivative of cosine will be negative. So you're just going to have minus r sine theta dr d theta dr, right? Then you have that. That's the derivative of x with respect to r, which just basically give us this. And the derivative of y with respect to r, that will basically give us derivative of r, it's 1. So we're just going to have sine theta. Remember, I'm applying the product rule right there. So you have sine theta plus r. The derivative of sine is cosine. Then you have cosine theta d theta dr. Then you have stuff like this. Dx dr is this, dy dr is that. Well, so you have those two differential equations right there. So now, what happens is that we're going to evaluate it as theta tends to approach 0. What happens when theta tends to approach 0? If theta approaches 0, cosine theta will approach 1, because we know that cosine, as it gets to 0, the graph basically approaches 1. And then sine will basically approach 0. Right, in that sense. Sine of 0 is just basically going to be 0 in that case. So we're going to shoot it to approach 0 in that case. So we're just basically going to have dx dr will just basically be equals to 1, because 0 multiplied by the whole of this will just basically be 0. And then dy dr, let's look at what happens. Dy dr, this is just gonna be 0. And then this one, cosine, will just basically, so what I'm basically doing is that I'm taking the limit when theta goes to 0 in both cases, for this case of x and this case of y. So in this case, this one is just going to be 0. In this case, cos theta, it's 1, so you're just going to end up with r cos theta is just going to be 1. So you end up with r d theta dr. So then here we get that dx equals dr. Here we get that dy equals, that means that you have to basically multiply both sides by dr, and then you have this, and then you have that. So dy just basically going to be r d theta. Then you have dx dy. So when you multiply them, dx dy or dy dx, the multiplication doesn't really matter. What matters is how you'll be integrating. If your transformation is that you want to start with theta, then that's where your order will basically matter, especially when we are coming to the bounds right there. When we're coming to the bounds. And then in this case, we say dx dy. That's just basically going to give us the multiplication of this will be dr by r by d theta, which is just going to be r d theta or r d theta dr. Those values will the order will basically depend on your boundaries for integration, whether you would like to integrate with respect to theta first or with respect to r first. So I'm just going to say r d theta. So that's basically that. And most of the time, this is dx by dy. A small change in x multiplied by small change in y. A small change in the base, and small change in that. So that's just going to be like a small change in area. So that's just going to produce dA. So we know that dA will basically be r dr d theta. So that's what we have. So now whenever we solve this type of polar coordinate system, this type of integrals that you have, transforming to polar coordinates is it's a simple way of solving an easier integral. It basically simplifies that integral. Okay, so now let's look at a few examples. Okay, so let's look at number 11 right there. Let's look at question 11 right there. So in this question, what we basically have is that you try to evaluate this double integral right there over a region R, whereby R is the region in the first quadrant between the circles with centers at the origin and radii 1 and 3. So basically we have something like this. So we want to find the double integral over a region R of sine of x squared plus y squared. Okay, sine of x squared plus y squared dA. So in this case, R is the region in the first quadrant between the circles with different radii. So then you have a circle with a radius of 1, and then you have a circle with a radius of 3. But notice that we're only focusing on the first quadrant, meaning that we're focusing only on, let me just shade the region. We're only focusing on this part of both circles. So we want to find that. So basically in this case, our integral is going to become easier because we're going to switch to polar coordinates. So let's do that and find what actually happens. So since a full circle corresponds to an angle of 2 pi, this is basically 1/4 of that. Since you have quadrant 1, 2, 3, and 4, this is basically 1/4 of that. So we end up having to divide 2 pi by 4 right there. So we end up with an angle of pi over 2. And basically, if we measure our angle starting at this point, we basically just have 0 right there. So we begin at 0. Our angle starts at 0. So basically, theta will start at 0, and then we go to pi over 2. That's just basically 0 all the way up to there. Now let's look at R, what actually happens with R right there. R in this case basically just starts from the smaller circle right here, going on to the larger circle right there, which just goes basically from 1 to 3. Basically goes from 1 to 3. So then from there we just basically gonna have our double integral. If you're gonna start with R, we're basically moving from 1 to 3, and if then follows theta, then you basically have 0 to pi over 2. So in this case, then we have sine of r square cos square theta plus r square sine square theta, because basically we just replace x with r cos theta and y with r sine theta, but because they are squared, then you square everything there basically. Then dA basically becomes r dr d theta. Okay, so then from here, since you notice that you can factor out an r square, and when you factor out an r square, you end up with cos square theta plus sine square theta. You basically end up having to have like 1 right there. So you end up with 1 multiplied by r square. And that's just basically going to be r square. So you end up having to have the integral from 0 to pi over 2 of the double integral of that of sine r square r dr d theta. So in this case now, you're going to have a u substitution there. Let u equals r square. Then du will basically be 2r dr, or just that du over 2 will basically be r dr, which is just basically what we have right there. So we replace, so then we replace r with u, and then we're going to change our bounds right there. So if r is 1, then u will be 1 square, which is just going to be 1. And if r is 3, then u is going to be 3 square, which is just basically going to give us 9. And then basically you end up having to have like sine u, then you have du over 2 d theta right there. Then you have 0 to pi over 2. Then the integral of sine is just going to basically be it's basically going to give us just negative cos, right? So from there we basically have the integral from 0 to pi over 2 of minus cos. So we basically going to have negative cos 9 plus cos 1. Then you divide that by 2, then you have d theta right there. Then you just integrate with respect to theta. This thing is just constant, so you can take it out. So you basically end up with cos 1 minus cos 9 over 2, and then the integral 0 to pi over 2 d theta right there. So basically then you just have like cos 1 minus cos 9 multiplied by pi over 2. If you evaluate this integral, you just get pi over 2. So then from then you just have 4 right there. So you have pi into that. So that's just going to be the answer in that problem. So similarly, you can work out number 12, right? It's nothing, it's, as long as you know what you're doing and you know the polar coordinate transformation, this thing should be basically easy. So from then, number 12, if we look at number 12, we have this double integral right there, where r is the region that lies between the circles x squared plus y squared equals a squared, and x squared plus y squared equals b squared, where with 0 being, with a between 0 and b. So this thing right here, it just basically tells you that this is the larger circle. That's what this thing basically tells you, that the larger circle is of radius b. So it's just the same problem, but now that you just, okay, let me just write the formula for that. So let me just do this. Let me just draw that region that lies between the circles. So now you have the inner circle with radius a. So you have the outer circle with radius b. Forgive my sketching, but as long as you get the idea of what's happening. So, okay. So now r is the region that lies between. So then we just basically look at this throughout. So this is basically the region that you are, it's basically like you're integrating through something like a donut. Well, yeah, kind of. Then from here, this basically tells you that r will go from there. R will basically go from this one to there. It goes from A to B. That's your new R. It goes from A to B. And then theta, since we're integrating throughout all over that thing, we know that a cycle corresponds to an angle of 2 pi. So we basically start here at 0. Then we move up, this is pi over 2, then we move there, that's pi, and this is 3 pi over 2, and then a full cycle corresponds to an angle of 2 pi. So we go from 0 to 2 pi right there. So basically this thing, I'm just going to write a formula for that. So number 12, you just basically have something like this. If you're going to start with, let's say r dr d theta. So you basically have r going from A to B, and then you have theta going from 0 to 2 pi right there. And then y square will just basically be r square sine square theta. And since you have x square plus y square, you know that that's just going to be r square, right? Because you end up having to have x, you're going to have r square cos square theta, and you have r square sine square theta factor out an r squared, then you end up with cos squared plus sine squared. That's basically 1. So you basically end up with r squared, and notice that these two will basically cancel off, and right there you end up having to have like the integral of r, because for the first integral theta will be constant, so that means that you're basically looking for the integral of r dr, then that's just going to be r squared over 2, then you take it from a to b, and then that integral, this thing is multiplied with the integral from 0 to 2 pi of sine squared theta d theta. And I hope you remember how you integrate sine squared theta. You're going to convert this to a double angle, so you're going to have a 2 right there, and then you're going to have a half outside, and 2 sine squared theta, if you remember the formulae for cos 2 theta, we basically have something like this. Cos 2 theta is basically just going to be cos squared theta minus sine squared theta, and it's also the same as you're just saying 2 cos squared theta minus 1, or you basically have 1 minus 2 sine squared theta. So you basically have something like this, but now we have 2 sine squared theta. So if you solve for 2 sine squared theta, that will be 1 minus cos 2 theta. So the solution to that one will just be half, and then basically just 1 over 4 into b squared minus a squared, if you evaluate this thing right here. And then from then, you multiply with the integral from 0 to 2 pi of 2 sine squared theta, which is just going to be, wow, oh, I didn't write that down. 2 sine squared theta, take it this side, and you take cos 2 theta that side, so you have 1 minus cos 2 theta. You have 1 minus cos 2 theta d theta. So from there, then you just work out that integral right there. So then you basically have b squared minus a squared over 4 multiplied by the integral of 1 with respect to theta will be theta. The integral of negative cos 2 theta will just basically be negative sine 2 theta over 2. And then you basically evaluate that from 0 to 2 pi. But what we know about sine is that if you take a period of 2 pi and you just smash it into sine, it will produce 0. And sine of 0 is 0. So this thing doesn't really make much of a difference in this case. So you're just going to look at theta. So you end up having 2 pi. So the solution to this thing is just going to be, it's just going to be 2 pi multiplied by b squared minus a squared over 4. Then this 2 will take out a 2 from here, then you have a 2. So you're basically just going to have your answer being pi into b squared minus a squared all over 2. So that will be the solution to number 12. You can look at number 13 as well, but the thing is just now you know polar coordinates, so it's just going to be that. Okay. I'm gonna do 13, and you just can do the remaining of the problems of polar coordinates, but hopefully I just hope that it's clear of what basically happens when you deal with polar coordinates. So we have a region D right there, so you have a double integral over a region D of e to the power minus x squared minus y squared. Another thing, don't let this exponent scare you, so because okay. So, where D is the region bounded by the semicircle 4 minus y squared, what do you see here? You can already tell that the radius is going to be 2. One of your bounds will have that. Okay, that's okay, by just looking at the thing, you can identify that. But it's easier to just sketch. So we have a semicircle 4 minus y squared, right? So if we have 4 minus y squared, we basically have something like this. If x is 0, y will either be plus or minus 2. If x is 0, y will be either plus or minus 2, right? So you have minus 2 and you have 2 right there. Okay, so notice that in this case x cannot be negative, because the square root of something should always produce a positive answer. So that already tells you that your semicircle is here. Your semicircle is basically here, where this one is 2 and this one is minus 2, and this one will just be, this doesn't really matter, but it's just going to be 2. I mean, where y equals 0, yeah, x is basically 2, but this value doesn't really matter. So now let's look at what actually happens. We start from, remember your angles are measured anti-clockwise, so you start your measurement from this point, and this angle, if you start there, it's negative pi over 2. and then you technically go all the way up to pi over 2, right? So that's one thing that you should keep in mind. And then you just do the same transformation right there. You have the value of r, the radius is basically 2 if you average this 2. So basically your origin is just this one, and from then you just, okay. So you have r going from, can the radius be negative? No, the radius should always be positive. So you have r going from 0 to 2. Cannot have a negative radius. Okay, so then from then you have theta going from minus pi over 2 to pi over 2. And I hope this one is clear of how you measure your angles when you have something like this, because it can get tricky when you have cases like this. So you replace x with r cos theta, but notice that you can factor out a negative right here, right? If you factor in a negative, you end up having to have r square cos square theta plus r square sine square theta. And then you have r d theta. Then you have something like this. Notice that you can factor out an r square as well. Then you have cos square plus sine square. Cos square plus sine square right there, that's just going to be 1. So you end up having to have like this integral from 0 to 2 minus pi over 2 to pi over 2 of e to the power minus r square r d theta. Then as you can see, this is a substitution type of question. It's a substitution type of question, so you can let k be minus r square. So if you let k be minus r square, then you have dk equals minus 2r dr. Then you can take a negative 2, then you have dk over minus 2, basically giving you r dr, and r dr you have it there. So then you basically have the integral from minus pi over 2 to pi over 2. Then you're going to change your bounds right there. And if you change your bounds, if r is 0, k will be minus of 0 square, which is just going to still be 0. And you plug in 2, then you basically have minus 4 right there. Because 2 squared, that would be 4. And you have a negative sign right there. So you end up having to have e to the power of u over du over minus 2. Why am I saying uk? Then you have dk over minus 2 d theta right there. So what do we know about e to the power of k? The integral of that with respect to k would basically remain the same, right? So you have the integral from minus pi over 2 to pi over 2. Since this thing is independent of theta, you can express these two integrals as the product of them. The product of that integral with respect to theta and that integral with respect to k right there. So you have minus 4, and remember you can basically have e to the k over minus 2 dk right there. So you can just express it like that. So the integral of that will just basically be theta evaluated from minus pi over 2 to pi over 2. To pi over 2 right there. So then from then you just have the integral of this one, which just be the same. The same thing, 0 to minus 4. Then you have that. Then you evaluate this, you're basically just going to have pi over 2 minus into negative pi over 2. Then you just have pi. And then this one, you're just going to have e to the power minus 4 over minus 2. Then the lower bound you plug is 0 there. Then you're just going to have e to the power of 0 will just basically be 1. And you have negative 2 there. So basically then you end up with something like pi, negative and negative, that will give you positive. Then you have positive 1 over 2. Then this one will be it will have a negative right there, so you'll have minus 4 minus e to the power of minus 4 over 2 plus 1 over 2, which you can just basically simplify to just pi over 2 into 1 minus e to the power of minus 4. So basically that will be the solution to that one. Okay, so I want to look at this one because most of you might get confused with number 16 right here. When you have something like this, okay, so there's no need for me. They stated that it's a circle. Okay, some of you might not see it because you'll get scared by the 2x that's there. But yeah, the whole point was that it's also a circle right there. So then you just remember, they say it lies between the circles. Okay, maybe I can like show you how you get your. Okay, so how do you get this? They say it's in the first quadrant. So basically what you have is you have a circle with radius of 2, being x squared plus y squared. This is the circle centered at the origin. Okay, and the second one right there, you just have x squared plus y squared equals 2x. I really wish they didn't just say that this one is a circle as well. I just wanted to see. It would have been interesting to like kind of like identify. Okay, so now you have x squared minus 2x plus y squared equals 0. So what you basically do is that you complete the square. Half of 2 or half of minus 2. Half of minus 2 is minus 1. Minus 1 square, that's going to be positive 1. So you're just going to add 1 on both sides. Then you have that plus y squared. This will basically be equals to 1 because 0 plus 1 will just be 1. Then you just basically have x minus 1 square plus y square. This will basically be equals to 1. So you have an inner circle of radius 1 and you have an outer circle of radius 2. So basically my sketches aren't really that great, but you have a circle centered at 1 0 there. That's the center of that, and you basically have something like this. And then you have another circle of radius 2 centered at the origin. Just gonna be something like this. Okay, like I said, my sketches aren't really that great. Yeah, I think that's pretty much it. Minus 2, 2, 2, and okay. You're gonna have to forgive my sketch, but basically the outer circle is that it has a center at the origin, and the other one is centered at 1 0 right there. So then you're just basically looking for this region right there. And with number 15, just because you see arctan doesn't really mean that it's a difficult question. It isn't. Yeah, it isn't. So but let me do it because like I see like something is interesting right there, because here you have the integral of arctan. You have a double integral over region R of arctan y over x dA. So when you have this, and they say that that region R, it lies between it's where x squared plus y squared is between 1 and 4. So okay, let me just tell you something. When you have this, just express it in the form of 2. Just imagine like you have 2 circles. The other circle is x squared plus y squared equals 1, and the other circle is x squared plus y squared equals 4, right? It's easier to interpret it that way. And now let's just, and then I'm going to come to this one. Let me first start with that one. You have x squared plus y squared equals 1, and then you have x squared plus y squared equals 4. So you basically have one with the radius 1 and the other one with the radius of 2. But now they further state that y is greater than 0. So immediately when they say y is greater than 0, just know that you're basically looking at the first and second quadrant, because anywhere less than here, it's where y is less than 0. So we're looking for y greater than 0 right there. So we're looking at the first and second quadrant. And they further state that x is greater than y. In order to interpret that, firstly, draw a line y equals x. If you draw a line y equals x, you have something like this. Y equals x. Okay, so here we can tell that in this region, that's where x is greater than y. In this region, that's where x is less than y. So they further stated that this is between the 2 circles. So we're looking between the 2 circles and also looking for where x is greater than y. So that basically tells us that we're looking over this region here. I'm just going to shade it. We're looking at this region right here. So basically we're just looking. Okay, so then now you know what's happening. Okay. The thing that's going to change here is just only finding theta. R still remains the same. R goes from the circle with the radius of 1 to the circle of radius 2. That's just basically what happens. The square root of 1, it's 1. The square root of 4, it's 2. So we already know that R goes from 1 to 2 because that's the region between these two. But now the angle of theta changes now. But okay, we are starting at 0. We know that here it's where theta equals 0. Let me just write that. Theta is 0. Here theta is pi over 2. And here theta is pi. And then here it's 3 pi over 2. And you're just going to progress like that. Okay, so now how we find our angle will depend on this one. Let's say in this case y equals x exactly. It's this line right here. Y equals x. It's gonna be a line, but you remember that the equation is basically mx plus c, but we don't care about the c. My focus is here with the gradient. In this case the gradient is 1. Remember the formula from back in high school right there? So you have tan theta equals the gradient, and in this case will just be 1. So you have theta equals arctan 1, and arctan 1, you need your answer in radians right there. That's just gonna be pi over 4. So now our angle theta goes from 0, because we basically start there, and then we go to pi over 4. Okay, then you have arctan, then you replace y with r sine theta, and x with r cos theta. Then something cool is about to happen though. So you have r d theta. So you have something like that. So you end up having to have something like this: the integral from 0 to pi over 4, 1 to 2 of arctan. Notice that the r's will cancel right there, and then sine over cos, that's just tan, right? Tan theta, r d theta. But now, tell me something. This is a function composed at an inverse, or a function composed at its inverse, or the inverse composed at that. So basically, if you have a composition like this, the inverse into a function, or the function into an inverse, we know that's just going to produce theta. Notice how everything just gets simple and simple like that. dr d theta. From then you can just work out this integral. First you integrate with respect to r, then you basically, since r and theta can be split in this form, so you basically, let me just write that. You have the integral from 0 to pi over 4, of theta d theta multiplied by the integral from 1 to 2 of r dr. You can express them as the product of like that, because they're independent. Well, if you did that, you know that. Okay. So from then you end up having to have theta square over 2 taken from 0 to pi over 4, and then you have r square over 2 taken from 1 to 2. Then you have something like that. Then you're just gonna have pi square over 16 over 2. That's just gonna be over 32, and you plug 2 there. You're just gonna have 2 square, that's 4. Okay, so you have 4 over 2. Then from there, then you subtract the lower bound, which is just gonna be 1 square, that's 1, so you have a half right there. Okay, so then you have pi square over 32. 2 times 2, that's 4. 4 minus 1, that's 3, so you end up with 3 over 2 right there. And then you end up with 3 pi square 2 by 32, that's just gonna be 64. So that will be the solution to that one. Okay, so thanks for watching. Don't forget to share and subscribe right there. And like as you can see, these problems are basically easy. You can try this ones as well. Okay, but it's just through interpretations, and I hope you get polar coordinates. All right. Okay.